Everyone, welcome back. So let's try another example, this time dealing with pitot probes. So on a plane, you might see these look kind of like little mini wings, but they're not wings, they're actually a pitot pressure probe. And so when an airplane was flying at a standard altitude of 10,000 feet, this pitot probe measured on it was measuring a pressure of 2,220 pounds per foot squared. Now, it was flying at a high subsonic speed that was greater than 300 miles per hour. Subsonic helps us say, okay, we don't have to worry about shock waves here. And we're going to try to figure out the velocity of the airplane. So how do we do this? Well, first off, we need to get some stuff from the tables. So from Appendix C in your textbook, if you're using Anderson, for a height of 10,000 feet, we get that my pressure and temperature would be the following. So 1455.6 pounds per foot squared and 483 Rankine. That's pretty cold. And now I can start using my isentropic relations. Now, how do I use that? Well, what you need to realize is that your pitot pressure probe does not measure pressure, it actually measures total pressure. So that right there, that is P naught. And since I know that, I can then figure out T naught. Like, why am I figuring out T naught? It's all of this, we're trying to go back to this equation from earlier. So H naught is equal to H plus V squared over 2. So I can just get that into the temperatures. I can solve for this velocity component. Okay, so we know our stagnation pressure because that was given in the problem statement from our pitot pressure probe. We looked up what the pressure would be for standard altitude. And so we plugged it in. And we get that the temperature would be 544.9 degrees Rankine. So whenever you see your pitot pressure probe, remember that is a stagnation or total pressure. It's one of the reasons this little thing right here is going to bring the flow to a stop when it enters. And because it brings it to a stop, it is now going to have the stagnation conditions. Okay, so now we can calculate the velocity. So my total enthalpy, or stagnation enthalpy, is equal to my enthalpy plus the velocity, or I should say the kinetic energy component. Now for a calorically perfect gas, I can say that my enthalpy is simply equal to the specific heat at constant pressure times temperature from both of those. I know my temperatures, I know my specific heat, which means I can now solve for my velocity. One thing to be very careful of here, this is English units, which means we have to use the specific heat in English units. And I would definitely write this down so you don't have to go find it again. It's 6,006 foot-pounds per slug degree Rankine. It's not fun. And so I find from this that my velocity is 862 feet per second. You're like, why not miles per hour? Well, because I didn't want to have to convert it here at the end. What pops out of here will be feet per second because you got feet right here, and it's always going to be per second from this equation. I could probably get some very strange, terrible specific heat that would give me miles per hour, but that's just wonky. It'll be feet per second when it pops out. So if you need to convert it back, you can go ahead and do that. So that's it for this time. Just remember that when you have a pitot probe, it measures the stagnation pressure. Not the static pressure, but the stagnation pressure. So thanks for listening. See y'all later. Bye-bye.